So there are different ways to be drawing the diagram or the graph for what happens when cardiac conduction occurs in non-pacemaker cells, but this is mainly it. So the way I identify that the graph for the cardiac conduction or the action potential graph, the membrane potential graph, is for non-pacemaker cells, aka contractile cells, is by looking at the plateau phase. Now, if there is a plateau phase, then it is a contractile cell or a non-pacemaker cell because the plateau phase is characteristic for that. Now, we're going to be discussing the action potential of cardiac muscles and the action potential within the non-pacemaker cells. And for pacemaker cells, I'll make a separate video. But for non-pacemaker cells, you have to remember two main points that differentiate them from the nodal cells. So simply put, for cardiac muscle contraction, there are two types of cells that are involved. The nodal cells, which include your SA node, your AV node, sometimes the bundle of His. And now for the other cells, the non-pacemaker cells, you also have non-pacemaker cells or cardiomyocytes, contractile cells. Now those include your actin, myosin, your protein components. Now, for the non-pacemaker cells or the contractile cells, one thing is that they do have a true resting potential. Now, this is different to the pacemaker cells, which don't have a true resting potential. The pacemaker cells, such as the SA node, AV node, they're all almost spontaneously, consistently depolarizing and repolarizing. Whereas for the non-pacemaker cells or the contractile cells, they have a true resting potential, which is represented by a straight line on the graph, which is in here. And they also have prolonged depolarization. Now, earlier I mentioned that the characteristic phase is the plateau phase, and that plateau phase is what allows the contractile cells to have a prolonged depolarization. Now, the resting membrane potential of the non-pacemaker cells is going to be minus 90 millivolts. That's their resting membrane potential. Now, due to intercalated discs, there are connections that are existing between the SA node, between the nodal cells and the contractile cells. These connections are known as gap junctions, which are composed of intercalated discs. Now, these intercalated discs allow the transfer of cations such as Na plus or such as calcium and potassium, the transfer of these cations to a contractile cell. Now, transfer of these cations can encourage or cause the Na plus channels to open and for Na plus sodium influx to occur. Now, one thing I remember is contractile, just think contractile. So that reminds you of phase 2 being plateau. Okay? Now, there are different phases, but simply put, let's talk about this really simply. Firstly, you have the sodium channels open. That sodium channel opening causes Na plus influx, this causes depolarization. Remember, I said depolarization is making something positive. It's going from negative to positive, making it positive. Now, your Na plus influx is going to cause your sodium channel ions to open, is going to cause Na plus influx. And that causes this rapid upstroke here, which brings your membrane potential from resting membrane potential and brings it up due to the Na plus. This is also known as depolarization. There's depolarization, rapid depolarization. That's phase 0. Now, when you get to a point, essentially when you get to 10 millivolts, you're going positive, 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 positive. When you get to 10 millivolts, the sodium channels close, and the sodium channels close or they inactivate, and this is known as the initial start of the initial repolarization. Remember, repolarization is making it negative, so it's the start of the initial repolarization, inactivation of the sodium voltage gated sodium channels, as I've put here. Now, at this stage, because you already had such a positive um, membrane potential, now the K plus voltage gated K plus channels are like, okay, let's start some efflux. Let's start to bring some cations out, and that's going to be your potassium. Potassium's going to go out via these voltage gated potassium channels. So that's going to open. So your voltage gated potassium channels are going to start to open. Now, throughout this, some books are saying that calcium channels are open and these are slow calcium channels, or these are L-type calcium channels, which are causing slow influx of calcium, but it's really, really, really minute. So it's really, really slow. So let's just imagine that keeps happening, keeps happening, keeps happening. This graph says that the slow calcium channels are open